Awesome. So Evan, thanks for joining us today. I'm super excited about this talk. Um, I think all of us right now are very much interested in kind of how formal methods is going to change in this new like era of AI and interesting tools that are available to us. And you're doing kind of cool, fun work that's related to that. So I'm excited to see what you're doing and yeah, take it away.
Yeah, I guess just to, on that topic for a little bit more, I think when machine learning first got really hot, about like 15, 2017, people in PR were asking these kind of questions. And there were a kind of abundance of paper where it's just like, oh, let's just put ML and PR together, kind of like slap on this like bigrams. And then there was like a whole bunch of paper, and none of them are actually quite impressive, I think. They're pretty like derivative. Things really changed when kind of Copilot kind of model came out, right? And then essentially the problem that was very hard to um, solve before, we were very concerned with, can you have a model that generates a program that even parse? And these model can generate huge chunks of Python that not only parse but actually like execute, and it's like kind of correct. So it definitely changed. So what I'm about to present today, has its roots in some of the older style of programming by example and more like traditional program synthesis, but most of these are still very applicable to current generation of AI. I think it would be really helpful if more of you guys show your faces. I mean, I'm on the toilet, so I mean, there's nothing too shy about not showing your bedroom or, things like that. But it's okay if you don't. It just make my life easier to know that I'm interacting with people who are not bots, right? Because, anyway. So I think I'll just get started and we'll see how it goes. It should be fun. And I haven't given this presentation for a while, so part of it might be kind of a bit hiccupy, but overall it's a pretty well practiced presentation, so I think it should go well. So I haven't changed the date yet. So anyway, the the presentation is on pragmatic program synthesis, and the idea is we want to disambiguate programs by thinking about how an informed person would choose examples. Okay, so let's just quickly get into it. The goal is essentially introduce the idea of pragmatics using rational speech act, which is some kind of cognitive modeling of how humans communicate concept using examples. And I will show how you can make program synthesizers using rational speech act. And it's a technique that's actually very general. It'll apply to any programming by example domain. And then I will show how these kind of things might scale to larger domains. And then hopefully we can have some discussion on how it might be useful for some of your own works, right? Cool. So let's start. What is program synthesis? Broadly speaking, is a kind of a translation, right? You have instruction from human on one side, and then it emits code on the other side, which is executed with the computer. Okay, and so the first thing we may ask about program synthesis is what kind of instructions are we talking about? And so, of course, we need to talk about instruction using natural language. And then you could really think of this as a translation task where someone speak about maybe the syntax of the program or some clues about what the program might look like. And then that gets translated into the code on the other side, right? So 2 plus x translate to the function that's 2 plus x. And this is, fairly, well practiced and very powerful way of generating code because you can train all of GitHub, and GitHub contain kind of paired instances of comments to code. And if you train a autoregressive model that way, when you input in comments, you get code on the other side. And so, yeah, so comment to code pairs. But there's another kind of instruction, which is examples, right? And human use examples. And when I say examples, I want you all to think about test cases, right? So the idea is, can you find a program that passes the test cases? And so I will just give you some example why using test cases is still very useful in the current day of natural language. So imagine I want to move some toilet from one side of the bathroom. Hey, that's kind of fitting. I'm actually in the bathroom to the other side of the bathroom. And if I just say that, the computer might misinterpret it by just like moving it literally to the other side, and then you'll be kind of taking a dump while facing the wall, right? It's kind of a bit awkward. But if I give you a single example, to say, well, can you move the toilet to the other side like the first one? Then you can actually very easily disambiguate, right? So it turns out that sometimes using a few examples is actually a very powerful way of communicating something that's quite complementary to language. Okay, so what we're going to be talking about today is programming by example, and the idea is to think of it as kind of Sudoku like puzzle solving, right? Where you have some constraints about the input-output test cases, and then they come with a program that satisfies the test cases. Okay? And so some advantages of using example to communicate is that instead of specifying how the structure should look, right, the syntax, you're actually specifying the semantics of the program, right, like how it should behave. And then you have some kind of correctness guarantee because it needs to be passing on the input-output example. And it's also data free, right? It's so that's the thing I will elaborate a little bit more. There are these concepts of low resource language, which is essentially programming language that doesn't have a lot of exposure on the internet corpus. So large language model don't really know what to do with these programs off the bat. And so programming by example actually work very well for these low resource language. And how does that work is, we have these programming by example synthesizer, which is some kind of enumerate and check kind of paradigm. I hope all of you guys are very, very familiar with this, but I'll just like quickly go through. So the idea is the synthesizer taking test cases, and then it begins to enumerate a whole bunch of programs. And you can do this in however way you want, right? It could be just enumerate from short program to long ones. It could be using a constraint solver. You can use a probabilistic context-free grammar, or you could use a large language model, right? But the idea is as long as you have some sense of the space of program, it could be from a DSL that you write, or maybe some stylistic Python code, and you say, well, large language model, can you just generate me Python code that look like this? Some kind of prior program you can sample, and then you can check if they're correct, right? So yeah, and hopefully for it's clear for us here that this doesn't require a lot of training data, right? Like you just need a way to enumerate a lot of program and be able to check. Okay, and so here is the key problem we are resolving with program synthesis. Not what we're resolving is like a key problem, classic, right? It's ambiguity. So the idea is if I give you a program that goes from 2 to 4, then there are some intuitive guesses like 2 times x and x plus 2 on the left-hand side. And there may be some spurious program that's also map from 2 to 4, but probably not what a human would be happy with if your synthesizer gives you that, right? So that's a problem yourself. Yeah, sorry. So I have a question. Please go ahead.
Yeah, just real quick. Am I the only one who can't see the very right side of the screen, of the
Yeah,
slides?
I think it's just you, Levi. Sorry.
Okay, never mind. That's okay. Okay, it's cut off for me. That's fine. I can see this.
Okay, sorry. But yeah.
Yeah, it's working for me.
Do you
Which
know what
means
the
it
right
will
side
be
might look like? The
visible.
right side might look like this. Okay. Okay.
Yeah, but it will be visible in the recording on the bright side. So,
Okay.
so at least we've
Cool.
got that.
All right. Perfect. So, really, on a high level, this presentation is about how might you build a synthesizer that prefers the program on the left-hand side over the program on the right-hand side, right? So the more human intuitive, kind of intuitively what this means, or we can formalize that in a little bit. And so this presentation is about how to apply some finding in Coxside to resolve this problem. So here we will take a very quick detour on how human resolve ambiguity. So this is why I need y'all to share your screen here so that I can have some kind of votes, right? So let's hopefully this go well. And so here's a little game, and then we have kind of two concepts. You have A and B. And then essentially A is a concept that wear glasses, and B is a concept that wear glasses and hat, okay? And then I'm gonna ask you to play this game where I want you to assume the role of a speaker, right? So the idea is you're handed one of the concepts. So someone say, hey, please communicate concept B in this case. So the person who wear both glasses and hat. So imagine you're trying to tell your friend about the concept that wear both glasses and hat. But there's a catch. The catch is that you can only use one word. You can only either use the word hat or you could use the word glasses. And then you win at the game if your friend correctly point at concept B instead of A. So hopefully that's clear. And so the question is, if you were to communicate concept B to a friend, would you use the word hat or glasses? So I'll give you guys like half a minute to think about this problem, and then we'll kind of vote. Wow, more people. Brilliant. Okay, so can I have a show of hand for those who say hat? Okay, can I have a show of hand for those who say glasses? Okay, almost no one, right? Cool. So we both agree that if we're kind of a informative speaker, it's more likely we will use the word hat. Okay, so now I'm going to flip the script. Okay, so instead of playing the role of a speaker, you're the role of a listener. And so the idea is that someone who is informative in the manner that we just described, instead of using the word hat, they actually use the word glasses. Okay, and so the idea is that upon hearing the word glasses, and let's say we're all playing this game, were they more likely to refer to the person who's wearing only the glasses, or are they more likely to refer to someone who's wearing both glasses and hat? So I'll give you another like 30 seconds to think about this. So we're playing the role of a listener here. Okay, so can I have a show of hand for concept A, the ones who's wearing glasses? Okay, can I have a show of hand for B, someone who's wearing both glasses? Okay, cool, brilliant, right? So it kind of works, right? So what happened is that you were thinking about why didn't they say hat, right? So if they would have communicated B, they would have said something different. And so that's kind of the whole idea. You're recursively reasoning about someone's actually being informative, right? So we've done basically disambiguation by reasoning what the other speaker could have said, right? And so we're going to now formalize it into some math, which is what rational speech act actually is. And so the idea is we will kind of basically explain rational speech act on the computational level, on how it can use to disambiguate in the little game that we just played. And then we're going to apply these computational model to program synthesis so that the synthesizer may disambiguate in the same manner that we just did. Okay. And so the rest of the talk will look like this. Kind of timely because I was just at ICML presenting the last thing on this timeline. So it's actually kind of cute how it turned out. So we will talk about rational speech act, and then we'll talk about the first instance of applying it to program synthesis. So this is kind of older work from 2020. And the rest of the two works on the right hand is about scaling it to larger domains. Okay, cool. Let's get started. So let's see beginning what's rational speech act. Okay, so RSA, in short, RSA is an algorithm such that given a communication game M, produce a pair of human-like speaker S1 and a human-like listener L1. Okay, so what is a communication game or a reference game? A reference game is defined uniquely by a meaning matrix. And for us, since we're in the land of program and logic, we can think of these as logical consistencies, right? So 0-1 matrices rather than with floating point value like probability, although you could think of it like that, and that's perfectly fine. And so I want you to imagine a matrix like the one here. Don't imagine, just look at it, I guess. On every column, there is a different concept, and on every row is a different utterances. So, right, so we have concept A and B, and we have utterances, hat and glasses. And in the entries, there are zeros and ones that basically denote which utterance is consistent with which hypothesis, okay? And so, and then to play this game, we have kind of two players. We have the speaker S, that basically take in a hypothesis. So you hand the speaker a hypothesis, they return an utterance, and you have a listener L, which if you give them a utterance, it's trying to recover the hypothesis, right? So, and the game is successful if this pair can kind of recover the original hypothesis that's been given to the speaker. Okay. And then the idea of RSA is that by running the RSA algorithm, you end up with a speaker-listener pair that play this game well. So essentially, the RSA algorithm is kind of these equations on the left-hand side, right? And so I think we have enough time today to just kind of go to the details, and you will just learn about it in the next like 5 minutes, right? So just stay with me for a little bit. Okay, let's go step by step. So let's start with the literal listener. So the literal listener, so U here means utterance, and W here means hypothesis or program. And so the literal listener, given an utterance, will give a program that is proportional to some prior of program, but also needs to be consistent with the utterance. So think of this as the kind of the silly robot, right? That upon hearing the word glasses is going to be 50-50 on either of the hypotheses. So the idea is maybe you put a uniform prior on both of these hypotheses. And then since they're both consistent, then it's kind of like 50-50 kind of a split. And we, from the literal listener, we kind of recursively build up the pragmatic speaker. And the pragmatic speaker, if you look at the equation here, is that given a hypothesis W, is going to use an utterance U proportional to how likely is the literal speaker going to recover the hypothesis condition on the utterance. So on the kind of little comic on the right-hand side, right? So the person is really in their head really thinking about the robot as they're trying to communicate one of the concepts. And so kind of in the game, what we just play, right? If you give them the concept that word hat, they're going to use the word hat over the word glasses. And we can do this one more time, which is a informative listener, L1. And L1 is essentially the equation again, but kind of flipped one way around. And the idea is given an utterance, you're going to return the hypothesis W proportional to how likely is an informative speaker going to use that utterance to explain the hypothesis. So you're kind of building these kind of recursive ladder. And so if you do it this way, and then upon hearing the word glasses, you're going to return the concept that only have glasses instead of one that with glasses and hat. So these are the Bayesian equations on the left-hand side. And kind of practically speaking, how you might kind of compute this equation is actually quite simple. You just have a matrix, the mini matrix of 0 and 1, as we described earlier. And then to compute L0, you normalize the rows, and then compute the S, you normalize the columns. And so this is kind of a very easy way to kind of conceptualize the computation, right? So you normalize rows and column over and over, and at the end, you wind up with the informative listener. And if you look at this row, which is a conditional distribution, right? Upon hearing the word glasses, this model is going to give 3/4 the probability of concept A and 1/4 probability of the concept B. And so they have a asymmetrical preference over A. And so this is a computational account of what we intuitively did as a group earlier. So this is a purely computational model. And to run this model, all you need is the meaning matrix 0, 1 on the left-hand side, okay? And so some psych work that is good with you, okay, blah, blah, cool. And so to recap, right, is simply an algorithm that if you give it a 0, 1 matrix M and you just run this algorithm, you end up with a informative speaker S1 and a informative speaker L1, right? So this is kind of covered by these prior works. Okay, so now we're going to apply this to program synthesis. And the key question is like, does that even work? And so this is the most important slide of the entire presentation, which is a parallel between pragmatic communication and program synthesis. And it's very simple because if you set it up this way, instead of hypothesis like hats or glasses, you just have all program within your DSL. And instead of utterances like the word hat or the word glasses, you have all possible examples that you may state to constrain your DSL. And instead of 0 and 1 that we kind of made up, we can decide if example or assertions or test cases or whatever kind of logic key predicate you might have with the semantics of the program is actually semantically consistent with the syntax of the program, right? And so your entire kind of the definition of a programming by example space is defined by this giant program cross example matrix. And it's also a 0-1 matrix, right? So it begs the question, if we just run RSA on this, what will happen? Okay, so that's the crux of this work. So we take a mini matrix where you have programs on the columns and example on the rows, and we run RSA on it. We will be able to have some kind of pragmatic listener L1 that take in example and produce program. And if we just slap a human in concert with these pragmatic listener, hopefully that'll have some very good performance in playing the game, because the user is going to use example in an informative way to refer to programs, right? And then here are some pros. It's data free, right? So in the spirit of programming by example, this doesn't need any human data. It only needs the definition of the, I don't know, the semantics or the meaning of the of your domain, right? Just a 0-1 big 0-1 conceptual matrix M. And the unknown is that do humans even communicate better with these kind of synthesizers? So this is something that we do not know. And so let's find this out, right? So in this first work, we have a fairly simple programming by example domain. And every program is a grid, essentially. And then every example is basically a grid element at a particular coordinate. And so essentially we have a DSL that tells you essentially for every coordinate, what symbol you might put at that coordinate. So at coordinate 5, 5, it might be like a green pig or like a yellow chicken or something like that. And then they tend to generate these kind of rectangular patterns, right, with some kind of alternative colors. And then the example really is revealing to the synthesizer some input output, which is on this particular input coordinate, I need the output of this pattern, right? And so the idea is, can you, so mini matrix look like this, right? About 20,000 columns of programs and about 300 rows on examples. And 0-1 is essentially, well, you know, this program happens to have a red pig on the 2, 2 coordinates and so on and so forth. So it's a big kind of 0-1 matrix. Okay, and the communication game is this. We give the human a particular pattern to communicate, right? Which is kind of the semantics of the program of all input-output pairs of this program. And then the human give a few examples, revealing that to the synthesizer, and the synthesizer attempt to recover a program that's consistent with the chosen examples. So let's play a demo, right? This is all runnable in JavaScript. So hopefully this all work. So here are some patterns from the distribution of programs you may have. They look something like this. So let's try this particular pattern. So given the fact that you're communicating these like rectangular patterns, and the idea is you want to communicate this pattern using as few examples as possible, right? So imagine you're being very efficient in communicating using example. Given this pattern, and we can kind of drop some of the symbols onto the canvas, what kind of well-chosen set of example would you choose as a person? So just tell me something, and then I'll put them there.
So part of the pattern is the colors, right? So if we can do like, but we only have one red. Are we limited to one of each thing?
No, you can give multiple.
Okay. So we could certainly communicate some information if we just did like red, green, red. And I would probably choose one of the rows that's already part of the pattern just to maximize the amount of information or columns, I mean. I don't know if somebody has a more clever idea than that.
I think you would need at least 4 different positions. I mean, I think you need like a red pig in the upper corner of the pattern. You'd probably need a green, what is that, a bird or something?
Yeah, it's a chicken.
Okay. You would need a green chicken in the middle somewhere. And I think you would then need
You need
probably
a green pig. Yeah, on one of the ends has to be a green pig, right, June?
Yeah, that makes sense. I think you would have to be on the far end. So you want it on the other side.
Okay, so given these three examples, actually both robots were able to
Wow.
recover the pattern. But this is kind of contingent on the particular DSL that we use, right? So let's try a kind of a different pattern. Let's maybe like, how about let's try this one. So what would you give for this pattern?
I'll let someone else take it if they want to.
Yeah.
Does maybe defining the boundaries help? So like the top left, like the first or second column, green entry, yeah. And then maybe the bottom right, same thing, green, and then you need another contrasting one, so like a red tree in the second column, second row. And then oh, is
Yeah.
that it?
Yeah, that's it, right? Okay, so this is basically what end user also came up with when we run this test on Mechanical Turks. So the idea is that we, didn't tell them how to actually communicate, but using the boundary is like one of the strategy that the user, like after interacting with these systems for a while, they kind of came up with. And we didn't really bake into return program that match the boundary into our domain, right? This is just through kind of figuring out, like from the mini matrix, we computed the RSA algorithm on it, and that's kind of the human machine was able to kind of coordinate on these kind of conventions. And the idea is the white robot is a non-pragmatic robot. It's actually given a program that's consistent with the examples, right? Which is kind of reminiscent of programming by example system, where it's kind of very annoying. It's like, hey, I'm not wrong, but it's kind of non-intuitive. And it's not able to find it because given these three examples in my particular DSL, on average, with three examples, there's 10 programs that are all consistent with these three examples. And so the white robot is not able to disambiguate among those 10 things. And the blue robot is like asymmetrical in their response, and so it's able to pick the one out of the 10. Okay. So
what I'm kind of curious about is if you look at that same example, we had a lot of like striped patterns, but what if it was instead like a red fill inside? Could you add a red chicken on the like one up and to the left of the green chicken? Okay. So I was kind of expecting that to fill it in with a rectangle.
I
How would you
see.
communicate that?
Yeah, so maybe like something like this. And I don't think, I think this is maybe like this particular pattern is not in my DSL. So maybe that's why it was a little bit weird.
Okay.
Yeah. The DSL is a little bit bespoke. I have like ring-like patterns of like outside and inside thing for the shapes between the chicken and the pig, but I only have like stripy like colors for these things. So maybe that's, yeah, but it's like a little bit bespoke. But okay. So we were kind of demonstrating intuitively that it kind of worked, right? So just to make it more clear, we also run a human study to make sure that not just us have some kind of agreement with the synthesizer, but actually work on like multiple people. And so what we find is that compared to the literal synthesizer, which is the white robot, right? The blue robot, on average, you use like fewer examples to communicate. So on average, you use a participant on Mechanical Turk. So these are end users. They use like 4-ish example to communicate successfully with the blue robot. And they use about 8 symbols to communicate with the white robot. Okay. And then and we just ask them like which one you prefer more, and most people prefer the blue robot, right? So that's kind of like this, whatever we observed, oh yeah, this cute, that kind of seems to work, is like kind of true in general with the population of end users, right? Which is the thing that we really didn't know, is like, does this even work, right? So this kind of validate that, hey, that's actually like, it works. And so so the quick recap, right, for a particular kind of very simple PBE domain, we do have human that communicate better with a pragmatic synthesizer over a literal one. And that's kind of the key finding of this like first work, right? Is that, oh yeah, this actually works. Okay, so now let's think about how to scale this to a bigger domain because it's kind of toy, right? And so exact RSA is pretty intractable. So we have these like alternizing normalizations on these matrices, which makes sense for a 2x2 matrix. And for this work, I mean, it's already a little bit hard to run it, but it also, I had to use some caching and some, think of it as like a dumb version of like version space algebra to make it like even runnable on the browser. But what we have in program synthesis is like truly combinatorial domains, right? With like, and so how do we get it to scale to these like truly combinatorial domain is what we're going to talk about here. And so let's think about ideally how you might build a pragmatic or human-like programming by example at scale. And ideally you have infinite money. Well, if you open an eye, you kind of do, right? And then what you do is you just get human annotations, right? You give human to give you a large corpus of program and example pairs. And then you train a neural network that map the example back to the program at training time. And at inference time, when the user give you an example, since the robots are trained from examples to program, you just output. And then that's kind of how, when we say neurosymbolic program synthesis, this is kind of what we meant, like generally. You have a large data set of example program pair and you train a neural network that kind of do this mapping. And at inference time, you just run the neural network plus some kind of sample and check to make sure they actually pass the examples, right? So of course, right, it doesn't scale, it's very expensive and blah, blah. And so what we might want to do is to generate data through self-play. And so the idea is instead of building one robot, you can build two robots. One is a speaker and one is a listener. And the idea is that if this pair of robots can successfully play the game of recovering the original program, we say, well, good job, successful communication. I'm going to add this to the data set. And then I'm going to basically train both of these robots from the data set of successful communications, right? So clearly you can use this to generate infinite amount of data and use our ever cheaper compute resources to train these models. So doesn't seem like a bad idea. Except you run into this kind of convention issues, right? Where you have a code that's highly efficient between the robots, but the human can't break into it, right? And this actually happened in RSA as well. I'm just using a natural language example from like older, I think it's from Facebook, right? Quite a kind of what is it called? Like charming example, whatever. So, and so the key idea is instead of using successful communication as the criteria, we use rational speech act. And so I'm going to describe you how it works, right? So the idea is we're going to generate data not based on successful communication, but based on pragmatics. And the hope is that data generated this way is similar to how a human would have annotated the data. And the hope is that if you train, well, it's not a hope, it's a fact, right? If you have data that's similar to how human would have annotated, if you just train on that, you end up with a synthesizer that's basically going to work well with human at test time, right? Because that's kind of what the premise of machine learning is. And so I'll explain how to generate pragmatic data. It has two steps. The first is sample with some self-play, and the other is improve the sample with rational speech act. So how do you generate data with self-play? It's quite simple. You have a pair of a speaker robot and listener robot, and then you sample a target program. You give the target program to the speaker robot, which will generate some number of examples. And then you give this example to the listener robot. So from this example, the robot will infer this is a program. And from this example, it'll sample this is a target program, and you do that like multiple times, right? So now we have a kind of a set, right, of candidate program and candidate examples. And what we do is we're going to use this to construct a kind of a small meaning matrix over just a sampled program and examples. And so on every column, we put our candidate program, including the target program. And on every row, we put our sampled examples. And for every entry in this matrix, of course, we can use execution to get 0, 1 value for this small matrix, right? So instead of enumerating every program and every example in some large combinatorial space, we're actually using the speaker and listener to sample kind of a slice of our space in this kind of small mini matrix, right? And then we can, of course, run the RSA algorithm as before on this small matrix. And what we compute here is we actually compute the informative speaker, which is S1. And what we do with S1 is you are an informative speaker given the target program P. What is the best example that you can give? And then they give the best example E star. And what we do is we just kind of discard all of these computation, but we store the best data E star into our data set, right? And so it's kind of, we generate some data and then we use RSA to improve it and throw away all of the other part of the trajectory that are like not good. But it's kind of as an inference, we can choose from any games like the best one according to RSA kind of thing. And so it's really very similar to AlphaZero, right? The idea is you have like 2 robots playing the game, and then you do some computation at training time through sampling. And most of that computation is kind of like, whatever, I'm going to throw it away, but I'm going to choose the best one to add to my data set. So this is kind of a, like loosely speaking, like policy improvement kind of a thing, right? You have not so perfect speaker and listener, but through many, many sampling and some kind of RSA, you kind of, they can become better through kind of thinking harder, right? So, and so get this data, then of course we just train on these data over rounds, right? So these robots can get a chance to kind of improve with each other kind of over time. Basically I'll tell you essentially how to stop, right? So you can imagine you start with a dumb pair of like speaker and listener and you can improve, but we need a stopping criteria. So here we actually do collect a very small amount of human annotations, like a few dozen. And what we do is, at some rounds of the iteration, we're going to take the listener robot and see how well is the listener robot perform on this small set. And we kind of stop if it kind of, the performance gets kind of worse. So this is our kind of validation. So we validate with a very small amount of human data. And we stop if the performance with this small validation set is kind of at some kind of optimal, okay? And so we apply this approach to the, what is this thing called? Like some regex, structure regex. And this is by some folks at, I don't know, it's like Texas. It's like UT Austin, I feel, is that group. And then essentially for this domain, we have every regex from this DSL on the column of the mini matrix, and then we'll have literally any string of like 20 characters. So you can type whatever gibberish you want. And then so that's our mini matrix. And then there is a demo, we can maybe play with this, but basically the idea is that it seems to work fairly well. And so here are some blob kind of plots. And on the x-axis is the number of example given. So were you successfully able to communicate the regex with like 1 string or 2 string or 3 string, kind of like that. And the y-axis is like, is the top 1 program returned by the synthesizer match the program that you are handed to communicate, right? And then we see that our approach, which is the pragmatic one, worked really well. And then the literal robot, which is the blue line, is robust fill and like deep coder. It's like kind of the standard neurosymbolic technique that we kind of described earlier, which is you generate some random program and example pair and you train on that, right? And so you could think of this work as a strict improvement to the standard neurosymbolic program synthesis approach that just generate uninformative but consistent program example pair at training time. And what we're doing here is, instead of just being consistent with example and program, but they're also pragmatic. So they end up like communicating better with humans. So that's how we get this boost. And GPT 3.5 kind of doesn't work. And we also did a human fine tune. And so what we did is we collected, I think, like 400 program and example pair from CMU students. Bless them, they have to write strings to explain regexes. But it turns out if you fine tune 400 program, you can actually get fairly close to our approach, but it does require like a fairly, for regex, like kind of reasonable size, like human data, right? So this is kind of somewhere in the middle. I think for our like criteria for like these kind of stopping criteria, we only require like 40 program as a validation set instead of like the 400 program that you might use as like a training set, right? And so speaker become more human-like over rounds. So on the validation loss of the speaker, it gets lower and lower. That basically means in terms of perplexity, our neural synthesizer is generating example that more and more resemble the example that human would have given it. And here is a kind of a fairly visceral example, right? On round 0, this regex is essentially 3 or more 1, followed by 3 or more H, followed by 3 or more 1s again, right? On round 0, you use this string to explain this regex, which is, technically correct. It's like, okay, definitely pass the regex, but it's not as informative. But as you do these kind of self-play in later rounds, you really get these like robots that truly exaggerate the extremities of these regex, right? Somehow the concept 3 has become important and the concept of like a lot more has become important. So it's using these things over rounds. Yeah. Which is kind of like a number, like a concrete instance of these becoming more human-like over rounds, okay? So on this work, like lastly, we'll just quickly talk about where, like whenever you have a neural system that kind of function, it's good to think about where does all the smart came from. So I've been doing this thing with a lot of my work, which is we kind of track the provenance of knowledge, like where did it come from? And then we have 3 categories. One is some kind of existing knowledge that's freely available, you can download. And there's manual work, which is in this red box, which think of it as like graduate student coding time. And then you have this green box and it's generated, so think of it as like compute, right? So how does that look like for this work? For our neural kind of synthesizer, we use by T5 small 300M model from Hugging Face. So this is freely available. It's trained on some kind of internet corpus of natural language. I think mostly kind of the common crawl data set. And what we did to build the first iteration of synthesizers, right? So we have a kind of a self-play game that goes like getting better and better, but like where did the first synthesizer come from? So we actually had to do like the robust field line of work first. And we essentially use a structured regex from the prior work, right? So this is a DSL for regexes, which is roughly 1,000 lines of code. And we use that to generate a consistent program example pair that's like not pragmatic, and it takes about 30,000 to generate like 100,000 program example pairs. And then we're able to fine tune a non-pragmatic synthesizer using this kind of generated data from the DSL. And with our work here is we coded up rational speech act, and the training code is like 1,000 lines of code here. And with that, we're able to generate a 5,000 program example pair that's consistent, but also pragmatic. And that took about 5 hours. And fine-tuning on this model further, on this data further, we're able to get a pragmatic synthesizer, right? And for stopping criteria, we have 40 human annotated examples. So this is essentially kind of the breakdown of where all the smarts of this work come from, right? So we heavily leverage what's been pre-trained on the internet. And then we also heavily leverage kind of self-play, which is a form of getting smart by computation, right? And then we really try to minimize the human effort, which is in the red boxes. Okay, so recap, how do we scale? The idea is you can use some kind of self-play and like iterative learning. And then you just want to make sure that you're using rational speech act as a success criteria rather than just straight up round trip success, so that you don't have these convention problems. And so lastly, let's look at amortizing it with ranking. Basically, we can already scale this, but the work that we presented just now really require us the ability to fine tune these models, right? which is actually pretty difficult if you have a general model like GPT-4 that's like too many things. So you can think of GPT-4 as a sampler. So given some example, it might give you some consistent program, but the idea is like, can you use a simpler pragmatic model to kind of rank them without having to kind of fine tune the whole GPT-4 model, like from the other side. And the idea is, can we make RSA simpler, right? So RSA is actually a little bit complex computationally. I mean, the equations are simple, but to carry this out is a lot of kind of numerical computation, right? And as a consequence, that's why it doesn't kind of scale. And so what we're looking for in this particular work is a simpler interpretation for Rational Speech Act. And so and the idea is we're going to drop out part of RSA that are not so important for just top K ranking. And so the first thing we might drop out is let's forget about probability and let's only think about ranks, right? So if I hear the word glasses, I just care that you prefer concept A over B in any way possible, but I don't really care the particular probability that go with it, right? So the idea is instead of probability, let's just say, well, I just need some kind of listener that rank concept A above B, right? So this is the first kind of simplification. The second simplification we can make is, can we have a ranking that's kind of even agnostic to the utterance? So not just I prefer A over B when I hear the word glasses. What if I just prefer A over B overall without caring about the word glasses? So I will always prefer A over B. And the idea is upon hearing the word glasses, I would just essentially select, since both are consistent, right? I'm going to select A. And so I'm only going to use the utterances as a way of filtering what is consistent. And I'm going to use this agnostic global ranking of hypotheses to choose among the consistent one, which one to return. So these are kind of the two simplifications. And so that's the idea, which is, can you kind of approximate the top K response from a RSA kind of algorithm by having a example agnostic global ranking plus consistency? So can these two like simpler ingredients on the right-hand side roughly approximate the behavior of a pragmatic synthesizer on the left-hand side? And the, okay. Right. Okay. Well, maybe I say how to actually get a ranking. Okay. So one way to think about a pragmatic listener is that it gives you example dependent partial rankings. Okay. So given an utterance, it's first going to filter for hypothesis that's consistent with it, and then it's going to rank it, right? And so with the utterance U1, like over here, only these two hypotheses are consistent. And then it's going to do some recursive Bayesian math to figure out, okay, of the consistent hypothesis, like which one do I prefer? And then given a different utterance U2, there are a different set of hypotheses that's consistent, and I'm going to do some recursive reasoning to figure out which one is consistent, right? So the idea is with RSA, you have these like example dependent ranking. And what we want to do with a global ranking is that, can we have a single ranking that's basically consistent with all of these example dependent ranking on the left-hand side? And so what we're going to do is, can we distill these kind of example dependent partial ranking, kind of distill all of that into a single ranking that's not example dependent, right? It's not kind of a global ranking. And there are different ways you might do this. What we've done is, you could either basically want to minimize these kind of inconsistencies, right? So on the RSA induced ranking on the left-hand side, you have like W4 ranked above W3, but in the global ranking currently we have 3 above 4. So maybe you can swap them, right? And so this is exactly what we did, is that you can distill that by kind of just do some kind of annealing. So if you're in a domain where you could enumerate all the program, then you just start with some kind of random ordering of every possible hypothesis. And then you could think of the rank on the left-hand side are some kind of evidence that you need to be made consistent of. And then we kind of do a lot of swap. And so this is actually quite common, like a partial rank distillation problem, like PageRank kind of algorithm. But what we find more general is that we can actually use it to train a neural scoring function. And so the neural scoring function is essentially, it will take in a program and it will output a number between 0 and 1. And so it will allow you to project an infinite number of program into the number line at the interval between 0 and 1, right? And then at test time, you can use a score to rank. So it will give you like an implicit ranking over a infinite space of programs. So this is also what we did. And so what we find is that the global ranking approximates L1 really well to be effective with humans. So this is kind of, in the animal domain of what we just did, we actually have like human interaction data we get from Mechanical Turk. And so we can replay that data to do kind of a pseudo-human experiment. And then we find that, the kind of the annealed, like this kind of like a learned neural ranking function actually match the pragmatic synthesizer in terms of like how many example does it take to recover the program. So they actually match very closely in performance, in communication efficiency. And then it's also highly speedy, because instead of doing the pragmatic, like recursive reasoning, these kind of synthesizer is literally, you give me a set of consistent program, and then it's just like, I'm gonna give you a score for each of the program and then give you like the highest scoring one, right? And so you just get, orders of magnitude of speed up because you're no longer doing the recursive reasoning, you're just doing a score model. But the idea is that the score model is distilled out of the recursive reasoning. So think of this work as a kind of compilation where you could run kind of slow RSA at kind of compile time, and then you distill all the smart of it into a single global ranking, which is highly efficient, and you could use it at inference time. And we have another result, is a theorem that says that if you are actually communicating using a single example, so it's kind of like a special case, you only use like one pattern, then these two are actually exact. So you can always distill a ranking if you're only using one example. And there are counter examples that you can give. Like if you use multiple examples, this result no longer hold. But we've shown that, in practice, this is kind of empirically workable. So those are kind of the two results from this work, which is like, if you're only using one example, you can always find a ranking that's consistent. But if you're using multiple examples, the ranking come pretty close for the kind of the domains that we kind of played with. Cool. And so this is kind of concluding the presentation. So hopefully this is kind of a recipe for making pragmatic program synthesis. So the first thing to do a pragmatic program synthesis is write down your meaning matrix, right? Like what are your space of programs? What are your space of examples or constraints or whatever kind of logical thing? And then what is your semantics, right? Like how are you going to give a 0-1 predicate for a pair of program and your kind of semantic utterances you might want to give. And the rest is like fairly, do a small user study, right? So this is like 2019, I was helping out at a startup, and then I had these guys like train these things, and it was fun, right? So once you do a small-ish user study, you kind of need the confidence that pragmatic program synthesis actually work in your domain. And then you can think about how to like make it like kind of scalable. And then there are some like works that we presented both are reasonable way of scaling this up to like larger domain. Okay. And so, right, so future direction that some of us might be interested in is just there are other 0-1 mini matrices, right? So it could be, execution traces, assertions, partial programs, however program analysis fact you might want to derive with that you can speak of with some syntax of the program, right? And as long as you have a 0-1 mini matrix, then you can run RSA on it. And hopefully running RSA give you a listener that actually work well with how human would like to communicate using these logical predicates that you want to communicate programs. And on the more kind of cognition side, the last work we presented is a way to kind of distill the expensive pragmatic reasoning into like a ranking. So then is there some way to go from the mini matrix directly to a ranking that's like much cheaper without this kind of roundabout way? Is like what I'm pretty interested in. So either some kind of like alternative explanation of RSA that will allow you to get a ranking straight away rather than distilling it from an expensive process. That's it. Here are some folks. Most of this work is done remotely. I've actually just met Sal just like in May, actually the first time I see him in person. And most of these guys are all remote somewhere else. That's it. There are some backups. But yeah, that's the presentation. Thanks for coming, I guess.
Evan, thank you so much. That was super fun. Do you have a
Yeah.
couple minutes to stay on for questions?
Yeah, I can stay as long as you want. So yeah, just hit me with any question you want.
Okay, maybe I'll start us off, and then I think probably other people will jump in. How do we scale, right? So like if we want to do pragmatic program synthesis on a language that's, you know, non-trivial and big and frustrating, and your matrix is like way too big to have in memory, then do you have, if it's like, well, this is a secret and I'm working on it, that's fine. But if you have clever ideas to share, I'm very curious how you attack that.
I think I think both of the latter two work actually make it fairly general thing that you can do for scale. So like in the first sorry, it's just gonna scroll for a little bit. So essentially, one way to scale is don't look at the whole matrix. So that's kind of the actual key idea. So you can kind of sample like parts of it, because you know for any mini matrix of a PBE domain, most of them are zeros, right? Because like given an example, chances are it's not going to be consistent with your program, right? And so what you want to do is to really do some kind of informative sampling of a kind of a slice of that big matrix in which you can actually do kind of efficient computation over. And on the second line of work, what it has shown is that actually like a prior or like just some kind of ranking of program can actually approximate pragmatic reasoning pretty well. And those are very easy to do at, like those are like tiny ranking model that you can tune with a very small amount of data. And so what you can do is maybe just even get a small amount of human data and just learn a ranking from that. Like that's how I might want to do some of this work now, right? So instead of using the 40 kind of the, right, like, where is it? Like this part, instead of using this to like validate something, like one thing that you can do is maybe blow this data set like a little bit bigger and just try to learn like a human, like some kind of rank function over these things and see how well that work. And I wouldn't be surprised if it just worked really well. So the idea of a program synthesizer that's not pragmatic is that it's just going to give you like a random ass program, right? And clearly any way of organizing that randomness into anything that's have some kind of order is better than nothing, right? Like that's kind of the key like appeal of doing pragmatic program synthesis. Is like any ordering is better than no ordering. And so it'll give you an ordering, and wow, this ordering is actually have something to do with like how human would like to communicate. So that's how it's going to work like really, really, really well. And so that's kind of how scale my work, right? One is just don't look at the whole matrix at the same time. And the second one is that you can be just looking at orderings, like without thinking about the example. So those are both like two very powerful way of reducing that big matrix into like a much simpler space. Cool, yeah.
So I have a question. So how pragmatic is this actually is? Like how large of a program were you able to generate with limited human input? Like just for regex, for example.
Yeah, I think for regex, we is basically off of this particular DSL. So however complex this one is, the example I give, like you know, they look maybe something like that. There are some like more complex ones, but I think this is more of a like a limitation of programming by example onto itself. Once these regex get to sufficiently like long and complicated, you probably don't want to use example to explain them anymore, because even then like human couldn't figure out like what to give. And so this is a case where natural language is actually quite important as a like basically example. Like think about kind of a set of program that's consistent with natural language description and a set of program that's consistent with like example-based description, and you do like an intersection that's actually why like multimodal communication is so successful, because with these like multimodal instruction, you can like intersect the space and be very, very precise. And so, yeah, in theory, these model can encode regexes up to like 20 ASCII characters. So however complex you want that to be, but it seems that human might not be able to even communicate those. So that's kind of the issue.
So do you imagine like using formal specification, it's easier or harder compared to natural language?
Yeah, so I would run a user study. This is a cop-out answer, but it's also like a very honest, like down-to-earth answer. I have this meme, which is people who work on program synthesis have this sentence of program synthesis has a promise of ending end user, blah, blah, communicate program easier, blah, blah. And then you just ask them, okay, bro, do you actually run a user study? And they don't. And so basically all of that work who claim these approaches actually helpful, for me, they're all not very honest because they don't actually validate with a user study. And so I would so the way to do that is, yeah, like for a particular domain, does formal, thing like maybe static analysis or something like that help you communicate a program? Well, I mean, do a study, right? Like give some undergrad who knows programming, right, some of these tools and see if they actually have an improvement. And I think with like maybe 30 participants, you should be able to get some very strong like confidence intervals, and you can say something statistic with that population. So I don't know, like every communication domain is different. And so that's why, to keep ourselves kind of fairly honest, we need to do user study, which is, arguably very dirty and not that many people want to do it. And that's kind of how I make a living, right? Which is like not that many people want to deal with human, but I kind of do. So.
So sorry, I was not being very specific. So I was asking what, in terms of designing a system, so imagine like a system that takes natural language is going to be more efficient, or formal specification is going to be more efficient in terms of like learning large programs, not like generating large programs.
Yeah, I think there are two parts to this problem, and I think we should kind of okay, balloon, sorry. So there's two parts. One is in terms of like specifying something, and the other is, can you find it? And so there is a two-part. One is like giving the problem to someone to do, and the other is that problem just simply too hard and nobody can actually solve it, right? So this is always the kind of the difference between just kind of the cogsci just a communication game. It's like, oh, can you point at the same thing that I'm pointing to, versus actually what we do, which is like program synthesis, which is yeah, these are like perfectly good specification that kind of pin down the single program is like non-ambiguous, but like, our Z3 solver explodes or something. And so we have like this dual problem of like both like communicating something that's like, that's kind of precise. And also we need to make sure our synthesizer can actually, with sufficient compute budget, find something that satisfies. So let's talk about those two kind of separately, right? I think in terms of natural language, how it's being used right now is to find the easier search. So what you do is, before 2015, the way we do search is we have a landscape of program, and they're all kind of equal. Like they are either satisfy or they do not satisfy your spec. And what you do with natural language is that it gives you a biased kind of a landscape over that program, right? So certain program will become more correlated with some natural language descriptions. Right? So when you say like, oh yeah, the function should have something about plus and a map, like kind of a construct for processing some list, then yeah, that hugely bias certain program over the other, right? So I think natural language, how it's being used in kind of contemporary program synthesis, is that natural language is used to kind of bias the search over promising regions. And for pin down what is right and what is wrong, I think this is where these kind of more formal descriptions are very useful, because computer doesn't really understand formal correctness of natural language, right? Like when we tell a programmer, hey, this program needs to blah, 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 like that's actually like a formal contract, right? Like if you don't do that, I'm not going to pay you on Upwork. And so, but computer doesn't know that, but computer can execute test cases, right? Computer can do static analysis and assertions. And so in terms of like precision, I think like formal thing are very helpful. And in terms of like biasing the space and finding a solution, natural language is very helpful. So that's kind of modern program synthesis, I would say.
I had a couple of questions around kind of really basic ones. So one is around multi-agent systems and like things like AutoGen and Crew AI and so on. So how, in terms of the kind of the self-play that you had there with those two agents, have you seen any, have you tried anything that has more than those two agents? And have you used any of these other like multi-agent debate kind of protocols?
Yeah. I have not. I was initially a little bit skeptical of debates, but I'm also, I mean, this is kind of like a debate-ish model, right? But like in broader, which is like, can you, with a domain that has a clear right or wrong answer, can you generate with these large language models some trajectory, chain of thought like thing that leads you to the answer and kind of regress back on the trajectory that's successful? I haven't tried. I wouldn't be surprised if you could just turn like this entire work over here into some kind of prompt version of it, right? And if you just do maybe some like prefix tuning or something, it'll probably work very well. Like I'm very bullish on that just working. And kind of the key takeaway is I don't know at which time our group over here like started doing program synthesis because at one point there was a huge emphasis on like writing your own DSL and context-free sampler for a program. Don't do that, okay? Now everything is token. And so I would advocate for this new way of thinking about programming as a string of token, which happens to be executable, right? And these large language models are very good at syntax. So we shouldn't be worried about syntax at all. Like essentially, if you give them enough training data, they can massage over. And so, and then you can do these like, use some kind of open model, right? And you can do some essentially like RL, like cooperative RL, right? You have two agents. One is trying to communicate, the other one's trying to interpret and do something to see if you can improve those agents. And maybe one more takeaway I can say is, yeah, I guess just don't be married to DSL too much. It's just all strings now. I mean, in this work, we very explicitly only use like off the shelf like Hugging Face model, right? These are all like token things, right? And in general, a kind of if you know Kevin Alice, the dude who does like Dreamcoder, so the current understanding between me and Kevin is that Python should be the last language unless you have a pretty good reason. And JSON should be the last data structure unless you have a pretty good reason for it not to be. Like you need to justify why it's not Python. And so if I were to do this work all over again, I would probably just use a regex class in Python and I would like basically make them like even more general.
And second question is around things like fund search. So it came out like end of last year, and they, they like there was some, I think I forget the problem, but I think it was a cap or whatever it was. But basically, they tried to like they had an LLM synthesize like a ton of different potential like improved algorithms over the state of the art, and it turns out like they came up with an algorithm that beat the best that any human had, and it was like there was all this hubbub about it. Is there any kind of like incorporation of either objective functions or like the kind of Monte Carlo approach of just like trying, seeing like taking sampling this massive search space and then seeing what performs the best? Is there anything like that that can be incorporated here?
I feel that's kind of orthogonal, but that's definitely an idea that people have been doing for a very long time. And if you're familiar with like Alex Aiken's work on like super optimizing bytecode, it's kind of the same thing, which is you define a space of search and then you do, I don't know, like the most broad term we can do it, like you take all the way back, it's like you just do some like mutation and evolution algorithm, right? And then it's going to generate things that kind of like, well, it's like cute, but most of are bad. But if you are very good at constraining the system on like, oh yeah, these are like good and these are bad, you can always do that. And we've been doing that. And now it's just different kind of backend for exploring the space of program. And with honestly, I don't know, man, bro. Like, I think in like a year, you will see like debate for optimizing code or something. And then like pretend you are a bearded OS kernel writer, and the other person is, oh, pretend you are a stallman who hasn't taken shower and is very angry and you're critiquing the code. I don't know, right? Probably something will happen, right? But these are just all kind of generative tricks one used to come up with like program proposals. The crux here is actually like on the checking side. Like, how do you verify these codes are correct, and how do you validate that they're actually more efficient, right? But yeah, that has always been there. Just generate random garbage and check if they're good. And we have been coming with like increasingly more sophisticated way of generating things that are like less garbage over time, right? Before we're literally using a SAT solver, and who knows, that search space is like 99.999% of that search space is like absolute garbage, right? Like there's just like program you would never write. And what we have with large language model is that we have such a good prior of program. So maybe only like 99% of that is garbage, right? And it's only going to get better. So.
Yeah, thank you.
So
We
I
should,
yeah.
we should probably just do one last question and then call
Yeah,
it.
sounds great.
I have a general question about program synthesis. So I guess this is a good ending question. So in general, as you showed, like program synthesis doesn't really synthesize that large of a program. I don't think correct me if I'm wrong. So what do you see like program synthesis do like nowadays besides like generating like Excel macros and things like that? And do you see like a future where we can scale program synthesis?
Yeah, so that's a good question. I wouldn't use the word like small program or long program. I would use kind of program that are in your prior or not in your prior, right? So clearly in Copilot, we can say, give me a website that do blah, like a Facebook logging website. It'll probably generate like 400 lines of code with like CSS and JavaScript and right? It'll probably work, right? It'll like call some Ajax, blah, blah, and then like it'll work. And so this is not a short program, this is a long program, right? But what is kind of like simple about this program is that it's closed in its training data's like prior distribution, right? So I think the question here is, how do you train synthesizer? And I use the word train, like I really think like you should be always like having some kind of neural backend somewhere now, right? Like how do you train model that can not only write like standard program that's kind of common on the internet, but also like specialized program that are like more rare in distribution. And the way that work is there are different ways for which that work. One approach that I'm quite excited about is to do some kind of data efficient learning per domain. So this is a big problem with large language model is that they're very good like prior, they know a lot about like general human convention. So that's one thing they're very good at. The second thing they're very good at is like they're very good at translating they're very good at translating syntax, right? So you could give it natural language, it can give you JSON. Like literally don't ever write natural language parser to like little data structure anymore. You just write like 100 in context example and just use like in context with like GPT. It'll just work, right? Like it'll be crazy to write your own little like left recursive parser or like don't ever do that again, right? Like it's dead. So the idea is you can have these kind of data efficient learning algorithm that can you give it kind of maybe like 100 example of what a particular domain is, and then it just kind of figure out how to do more things in that domain. So that's kind of the big problem moving forward, which is kind of how do you, without too much human involvement, specialize these large model into something that's like particular with the domain. So something we're looking at is like ARC. So we know like the ARC kind of challenge, right? So can you, in a very data efficient way, teach computer how to take a input-output grid of a ARC puzzle and output Python that solves it, right? That's like a very challenging problem. And we only have 400 ARC problem to like build off of. So like how do those approach look? So these are like the way forward. Cool.
Very cool. Evan, this was great. Really appreciate
So
your
wait,
time.
now, give me the recording of this. I can just put it on my website or something. And I have all of your consent to put this up, right?
Yeah, so yeah, we're gonna probably upload it to YouTube, and then I'll send you the link if that's okay with you.
Oh, perfect. Cool.
Okay.
Yeah.
Perfect.
Thank you.
Awesome. Thank you guys so
Cool.
much. Thanks for coming.
Yeah,
This was
keep
a lot
in
of
touch,
fun.
right? So if anything,
Yeah.
I'll actually let me do
I can add you to the Slack if you'd like. Where
no,
we
it's
organize.
just add me on Twitter. It's this
Oh,
one.
perfect. Okay. All right. Everybody's got that. Okay. All right. Thank you, Evan. Have a great
All
day.
right. Ciao. Have a good one.
Okay.
Bye-bye.
Bye.